Hello, hello. Alright, so I think I'm live. Today we're going to read the paper Methods for Interpreting and Understanding Deep Neural Networks. So, this paper provides an entry point to the problem of interpreting a deep neural network model and explaining its predictions. It's based on the tutorial given in ICA SSP. I don't know what that is. Okay, it's an IEEE conference. It introduces some recently proposed techniques of interpretation along with theory, tricks, and recommendation to make most efficient use of these techniques on real data. It also discusses a number of applications. So this is a paper. The paper is, decently long. So I'm not sure if I'll be able to read the whole thing today, but it depends on how difficult the paper is to read. Just before we continue, just ensuring that, yeah, my voice is clear. Wait, now before everything else, reading research papers, and we'll copy. Yeah, I'll copy the whole thing. I push this. And I'm gonna push that. And I will do 24 and this in dot mark one. Who could methods for interpreting and understanding neural networks. I'm not fully completed to read the paper just now. Probably it probably will. But before that, we'll just do level one skimming, which means I'll just read the what I call it most important parts, which is the abstract. Oh, okay, which is the abstract and what do you call it? Conclusion. Right. So abstract is okay. Oh, this is abstract. The second part of the tutorial focus on the recently proposed layer-wise relevance propagation technique. Relevance propagation technique. I'll just ask this guy. Layer-wise relevance propagation is an interpretability technique designed to explain the predictions of deep learning models, particularly neural networks. Okay. Before I continue, uh, just want to ensure. I don't know if this is better or this is better. I don't know which is better, but yeah, I think this is. Right. Anyway, let's continue. Layer-wise relevance distribution output score of neural network backward through the layers of the input. Redistribute the output score of a neural network backward through the layers of the input in such a way that the relevance of the output prediction is preserved at each layer. I mean, okay, I don't know what it is. I have no idea, but we'll continue. We'll read them. Okay, this is like 2017. Okay, cool. That is not too old, and that is too old. Like anything before the Transformers. Whoa. Okay, no, thank you. Okay, introduction. We have the introduction. Preliminaries. Example of a neural network composed of many interconnected neurons and that assigns to an input X the probability of being associated with a certain concept W. See, interpreting a deep neural network, improving AM with an expert. Carter illustration of how the choice of expert affects the prototype. Hmm. Okay. Decoding function. AM plus decoder, AM plus expert, simple AM. This looks very good. And ground truth bot. Explanation for a bot. You take this and output this. Hmm. I think like when you input an image, this thing somehow explains that this is a reason why the model thinks that this is a bot. And similarly, this is the reason why the model thinks, okay, you get that thing. That's interesting. Function to analyze. Simple Taylor decomposition. Pixel wise heat map. Region wise heat map. Graphical depiction of the filtering mechanism. Here only what passes through the first two neurons of the second layer is further propagated. Only what passes through the first two neurons of the second layer, second hidden layer. Hmm. This two. Because of filter. Okay. LRP applied to what is LRP? Is it this thing? Yeah. Relevance propagation. Okay, I think this is this thing. Like filtering thing. I don't know. I'm not sure. LRP applied to convolutional DNN. You call it DNN, deep neural network. Nowadays we call it ANN, right? Artificial neural networks. Not sure how the literature calls it. Mm-hmm. Forward propagation and backward propagation. I don't know what is propagated backwards. Relevance? Though I don't know what relevance is. Yeah, I mean, what I do know is we are not finishing reading this paper today. Like, not short, right? Recommendation tricks. Okay. Oh, hello. Okay. Heat maps obtained by exploring fully connected deep neural network on MNIST. Highlighting in a large image pixel that are relevant for CFR. I don't know, man. CNN, what do I classify? Hmm. Application. Explanation for age is this. Explanation for gender is this. I don't know how this is a explanation for gender, but sure. Okay. Okay. Right. Now we'll start reading the paper. Korea University, South Korea, Germany, Korea. Okay. Deep neural network, activation maximization, sensitivity analysis, Taylor decomposition. Yeah, before I start, I just want to revise what Taylor decomposition is. Isn't it a way to approximate a function? A mathematical, no, it's not a Taylor function. Mathematical framework used in interpretability to explain the prediction of machine learning model. Okay. Mm. Taylor series explanation is this more formally. Okay. Um. Okay. It is based on the principle of Taylor series expansion, which breaks down a function into terms of derivatives. At specific reference points. In the context of machine learning, it helps to attribute the model's prediction to its input feature by expressing the prediction as the sum of the contribution from these features. Key concepts in Taylor decomposition: local approximation, feature contribution, first order and higher order terms. Hmm. Reference point: Taylor decomposition machine learning. It is often used to explain prediction of complex model like neural network. Often used to explain the prediction of neural networks. Hmm. Nice. Okay. So somehow Taylor series can be Taylor. It's not Taylor series. It's Taylor decomposition can be used to what we call predict neural networks. Hmm. Okay. Nice. Machine learning techniques such as deep neural networks have become an indispensable tool for a wide range of applications such as image classification, speech recognition, or natural language processing. These techniques have achieved extremely high predictive accuracy, in many cases on par with human performance. Today, yes. In practice, it is also essential to verify for a given task that the measured accuracy result from the use of a proper problem description and not from the exploitation of artifacts in the data. Uh-huh. Techniques for interpreting and understanding what a word has learned above have therefore become a key ingredient of robust validation procedures. Sure, interpretability is especially important in applications such as medicine or self-driving cars where the reliance is high. Okay. Um, interpretability, increase sharp. Simple models provide higher interpretability than complex ones. It's a common belief linear models or basic decision trees still dominate many applications for this reason. This belief also have a challenge by recent work in which carefully designed interpretation techniques have shred some of the most complex and deepest machine learning models. Ooh, okay. Kinda want to go here. Though it's going to be a tangent, isn't it? Deep inside science. Visualizing image classification. Hmm. Okay. I have to start reading this. Well, techniques for interpretation are also becoming increasingly popular as a tool for exploration and analysis in science. In combination with deep nonlinear machine learning models, these have been able to extract new insights from complex physical, chemical, or biological systems. This tutorial gives an overview of techniques for interpreting complex machine learning models with a focus on deep neural networks. It starts by discussing the problem of interpreting modeled concepts, and then moves into the problem of explaining individual decisions made by the model. The second part of the tutorial will look in more depth at the recently proposed layer-wise relevance propagation technique. The tutorial abstracts from the exact neural network structure and domain of the application in order to focus more on the conceptual application that underlie the success. Okay. In spite of practical success, one should keep in mind that interpreting deep networks remains a young and emerging field of research. There are currently numerous coexisting approaches to interpretability. This tutorial gives us a snapshot of the field at the present time, and it naturally somewhat biased towards author's view, as we hope that it provides useful information to the reader. As such, preliminaries. The techniques of interpretation have been applied to a wide range of practical problems, and various meanings have been attached to the term understanding, interpreting, or explaining. It can be useful to clarify meaning as we assign these words in the tutorial as well as the types of techniques we cover. We will focus on the tutorial on post-hoc interpretability. Why is that? Trained model is given, our goal trained model is given, and our goal is to understand what the model predicts. Katha. In terms of what is readily interpretable. Post-hoc interpretability. Hmm. Okay. Okay, sure. Also, using the word understanding. Also, when using the word understanding, we refer to the function understanding of the model. In contrast, our mechanistic or algorithmic understanding of it. That is, we seek to categorize the model's black behavior without, however, trying to elucidate its inner working or shed light on the internal representation. Furthermore, while some methods aim at reaching a comprehensive functional understanding of the model, we will focus here on interpreting the output of a deep neural network and explaining individual predictions. So the tutorial will make a distinction between interpretation and explanation. Okay. Interpretation is a mapping of an abstract concept to a domain that the human can make sense of. Examples of domains that are interpretable are images, text. A human can look at them, read them respectively. Examples of few domains that are not interpretable are abstract vector spaces, word numberings. A domain composed of undocumented input features. Sure. An explanation is the collection of features of an interpretable domain that have contributed for a given example to produce a decision. Okay. The features that form the explanation can be supplemented by relevant scores indicating to what extent. Okay. Practically, the explanation will be a real valued vector. Okay. The explanation can be, for example, heat map consists highlighting the heat map highlighting which pixel of the input image or strong input image most strongly support the classification decision. In NLP, explanation can take the form of heightened text, highlighted text. And I'm going to take a small break. Give me a sec. Yes, sorry about that. That went a bit longer than I expected to. Yeah, so we will be continuing interpreting a deep neural network model. This section focuses on the problem of interpreting the concept learned by a deep neural network. It's a collection of where neurons some is performed in the neurons of the network. I mean, just 1 second, just ensuring that your work. Whoa. Uh-huh. Neural network joins a complex nonlinear mapping activation function. The mapping is learned from the data. Oh, okay. As a whole function. Okay, cool. The mapping is learned from the data by adapting to the weights of each neuron is a technique called backpropagation. Error backpropagation. The concepts. Hmm. Anyways, physics. Okay. Learning representations by backpropagation. Yo, this is just backpropagation, isn't it? Okay. Building a prototype can be formatted within the maximization framework. Activation maximization is an analysis framework that searches for an input pattern that reduces a maximum model response for quantity of interest. Okay, this is the neural network. Machine learning technique that help researchers and developers understand and improve performance of neural network. Finding input that activates specific neurons. Okay. Okay. That's cool. Right. I don't know what I did, but it's something. Consider a deep neural network classifier mapping. Data points X to a set of classes. The output neuron encodes the model class probabilities. The prototype X star represent the class WC that can be found by optimizing maximized logarithmic just error between these two. The class probability model by deep learning deep neural network or function what the class probability model by the neural network are functions with gradient. This allows for optimizing the objective of gradient descent. The rightmost term of the objective is L2 norm regularizer that implements okay that's a regularization in short. When applied to the image classification prototype that take the form of mostly gray images. With only a few edges and color patterns, this prototype although producing strong cross response looks unnatural. I don't exactly understand what they're trying to like look for here. Anyway, improving AM. What is AM? Activation maximization with an expert. In order to obtain more meaningful prototype, the L2 regularizer can be replaced by a more sophisticated one called expert. The expert can be, for example, a model PFX of the data. This leads to the new optimization problem. Maximize log P plus log P of X. P of weights given X. He said WC. What is WC? Output. No, that's a output. Okay. Maximize output plus P of X. What is P of X? Input. Okay. Maximize. Find the. Oh, it's probably argmax, right? So what is the biggest X? I don't know, man. I'm not sure. These are all the what do you call it? Representations obtained by solving optimization problem, which is on the sum of the data by applying base all the newly defined objective can be identified up to modeling errors and constant terms as the class condition data density log. The density prototype will thus correspond to the most likely input X from the class WC. A possible choice for the expert is the Gaussian RBM. It can represent a complex distribution and has a gradient in the input domain. Its log probability function can be written as this, where the terms are learned from the data and comes in superposition to the original L2 norm regularizer. Okay, Gaussian RBM, can represent complex distribution and has a gradient in the input domain. And understand exactly what that means. Its log probability function can be written as this. And interpreting concepts such as natural image causes more complex density modes such as convolutional, these guys can be used instead, probably for images. In practice, the choice of an expert UFX plays an important role in determining the appearance of the resulting prototype. I don't know why I'm not able to copy well. You can copy all those, but I can't copy this. I can copy that too, but I can't copy like this. Maybe I can. I don't know why. What happened? Uh, Explain. Refinement of activation maximization technique by incorporating expert model PFX to generate more meaningful prototype. Activation maximization optimize this function. Okay. Oh, we are activating one class. And ensure, okay. Okay. So let's go here. Yeah, it's fine. One extreme goal expert reduces optimization problem to the maximization of class probability function. The other extreme is overfitted examples, essentially reducing optimization problem to the maximization of the expert itself. I mean, I don't exactly understand the whole thing, but I think I have an idea. So what this is what we try to activate a class by maintaining by ensuring that the x is like what reasonable. Okay, I mean sure. When using an AM for purpose of validating neural network model, an overfitted example must especially be avoided, as a latter could hide interesting failure modes. Okay, sure. I mean I understand exactly. Okay, oh, this is okay. Hmm. Well, this is the data. True would be this. This is outfitted. Okay, cool. A slightly underfitted expert B simply favor. Okay, favors image with natural colors. Cannot be can be ever be sufficient on the other hand. Corrected by the focus should be to prevent outfitting. Sure. Here underfitted expert we would expose optima potential distance from the data and therefore the prototype can be totally representative. I mean, I am not sure I exactly understand what is being like talked here, so I think I will read this part again tomorrow. Okay. Yeah, let's finish the section though. Pretty sure I have to read the whole thing, this section again. In certain application, data density model can be hard to learn up to high accuracy or very complex, such as maximizing them becomes difficult. An alternative class of supervised models are generative models. They don't provide the density function directly, but sample from it, usually via following two steps. Sample from a simple distribution, apply to the same decoding. I mean, I'm not understanding a thing. Oh, this is a really hard read, man. Even though like it is not much math heavy or some or anything. I think it's better if I read like a summary of this paper, man. and then like move into this thing. I'm not understanding a thing. Like it's not even close. Methods for interpreting and understanding. Okay. Deep neural network have achieved remarkable success in various domains, but the black box nature present challenge of trust, reliability, and accountability. This paper provides a comprehensive review of methods of interpreting and understanding deep neural network, categorizing into three main approaches. Categorizing what? Interpretability, probably. A feature-based, example-based, and model-based. Feature-based. This method focus on understanding the importance or influence of input feature on the model's prediction. Sally maps highlight regions that contribute most to the output. Oh, that is a fun part. We could stay here, honestly. Gradient-based methods compute gradient with respect to the input to determine sensitivity. Attention mechanism. We talk about attention. No. Do we have transformers? No. Is all you? No. I was looking for attention silent paper. Anyways, it's probably yeah. Anyways, example-based interpretation. These methods are specific examples to explain the behavior. Identify representative examples, prototypes, or minimally altered inputs. Compare predictions. Model-based interpretations. These methods focus on simplifying or visualizing the internal structure of deep learning neural networks. Layer-wise relevance propagation. Distribute prediction score back to input features. Back to input features. Right, so features gets a score. Hmm. I don't know, man. I have no idea. Activation. This is hard read, but okay, we will read it. This might take. I was expecting to finish this by like tomorrow, but this might take longer. Surrogate models use interpretable models such as decision trees approximate the behavior of deep learning neural networks locally. Hmm, that is fun, right? Using deep learning, I mean, tree models to approximate neural networks. That would be interesting. Challenges and open problems. Scalability. Many methods struggle with higher dimensional data. Okay, robustness. Interpretable interpretations may be sensitive to noise or adversarial examples. Just a universally accepted metrics for assessing the quality of interpretations. The author emphasized the need for robust, scalable, and domain-specific interpretability tools. I am just going to copy this thing into my into the this part so that I can read this soon again. Like summary from ChatGPT. Yeah, we will read that later. So I think I'm going to end the stream right now, and thank you for watching. So about this paper, I will read this paper. I don't know if I should read the paper again tomorrow or if I should jump to another paper especially like something in the references so that I can understand the paper better. I might do that. Yeah. I also have like a I mean, what do you call it? A Notion page where I write all the paper which I want to read in the future, near future. So yeah, this one. This is actually like live. Actually, you can just see this here. Here. So in this link. So I want to update this. This is not perfect, but I want to update this. I want to add more. So I probably add these guys here. Yeah. So I that's about it from me for today. And thank you for watching.